Okay, today is 5.6. We will factor what looks like unfactorable polynomials today using something called remainder and factor theorems and with the help of synthetic division. So we've learned long division, synthetic division. So these are going to help us factor 4 to 10 term or more term polynomials. Okay. First up is the division algorithm for polynomials. If f and g denote polynomial functions, and if g is a polynomial whose degree is greater than 0, then there are unique polynomial functions q and r such that, so what we're looking at here is just the division algorithm. Everything we've done so far with synthetic division and long division. When you have f of x divided by g of x, well, whenever you do any type of division, we always get a quotient, which is the q of x, plus a remainder, r of x, over a divisor, g of x. So this is just the normal division algorithm we're used to. Another way you could rewrite the division algorithm, though, is if you decided to multiply everything by g of x. So yeah, good. Sorry, I'm still getting used to this OneNote. Carl, the new updates broke my other OneNote.
That's
So
horrible.
now I'm using the
now
old
I know
school.
why all of mine say that something weird changed.
Yeah, like it won't sync or do anything. It's horrible. But the 2016 syncs, works perfectly. Great. All right. So like I said, if you wanted to change up the division algorithm, then you would multiply everything by g of x and end up with this new algorithm. F of x equals the quotient times the divisor plus the remainder. Okay. All right. And that's all going to come in handy when we start breaking down these polynomial functions, when we get there. Okay. Ugh, it's so awful. Okay. Get used to it, though. All right. Where r of x is either the 0 polynomial or a polynomial of degree less than the denominator, g of x. And again, above, f of x was the dividend, g of x was the divisor, q of x was the quotient, and r of x was the remainder. So nothing new. That is just the division algorithm we've been working with since we started long division and synthetic division. Okay. The next theorem is remainder theorem. Let f be a polynomial function if f of x is divided by a linear factor of x minus c, then the remainder is f of c. So what remainder theorem is telling us is that, hey, if you are going to use long division or synthetic division, and you want a way to check your remainder that you have the right answer, then go ahead and take that linear factor of c and plug it into the function. And if you did your long division and synthetic division correct, then by plugging in c, should give you the same remainder as you got by using synthetic and long division. It's actually pretty cool. So now we have 3 ways to check for a remainder: long division, synthetic division, or plug in by using remainder theorem. All right. So let's go ahead and practice that below. It says, using the remainder theorem, find the remainder if f of x equals x cubed minus 4x squared minus 5 is divided by x minus 3. Okay, so I'm just going to show you how this works. Let's go ahead first and set up for synthetic division. So since that's x minus 3, I'd put a 3 on the outside, and then inside I'd put my dividend. X cubed minus 4x squared minus 5. So 1 for x cubed, negative 4 for x squared. We're missing an x, so 0, and then negative 5. 3, 2, 1, 0. The 1 comes down, 3, and then we add, and then you get negative 1, negative 3, negative 3, and then negative 9. So here's our remainder of negative 14. So what remainder theorem says is, hey, let's go ahead and check if we have it correct. Let's see if we did the division process correctly. So with remainder theorem, all we have to do is say, what is f of 3? We take that divisor of 3 and plug it into the given function. And you'll get 3 cubed minus 4 times 3 squared minus 5. And this will give me 27 minus 4 times 9. So that's 36 minus 5. 27 minus 36, negative 9 minus 5. And look at that. We have the correct remainder by synthetic division, because when we plug that factor in, or that divisor into the function, we get negative 14. So it checks out. So remainder theorem is a way to check your work when you are using long division and synthetic division. Did you get it right? Okay. Any questions on that? All right. Well then, let's go ahead and try it for 2. So here, we'll do it again. I'll set up synthetic division. Negative 2, put everything in. 1, negative 4, 0, negative 5. The 1 comes down. You get negative 2, so that's negative 6. And then 12. And then negative 24. All right. And then you'll get negative 29 as our remainder. So we can go ahead and check that by saying, what is f of 2? Negative 2. And you'd have negative 2 cubed minus 4 times negative 2 squared minus 5. And negative 8 minus 16 minus 5. So negative 24 minus 5. Again, it checks out. We get negative 29 as our remainder. Okay. So that is, once again, remainder theorem. When using long division and synthetic division, if you want to know if you got the process right, then go ahead and take that divisor, plug it into your function, and if you arrive at the same, if your result is the same number as your remainder, then you have done it correctly. Okay. Any questions on that?
Is the process going to be same thing for long division, or are we getting to that?
Oh, very good question. The same thing goes. So this works for long division as well. I just didn't want to show long division. That would take too long.
Oh, okay.
Hot. All right, but it would. So yeah, again, so if you're doing long division or synthetic division, then this would work the same. But of course, it has to be by a linear factor of x minus c. Okay, all good? Okay. So a consequence of the remainder theorem is the factor theorem. So I think I may have mentioned it when we were doing synthetic division, but if you're ever dividing by a linear factor of x minus c and you get a remainder of 0, this means that x minus c is a factor of the polynomial. So that's what we're stating here. Let f be a polynomial function, then the linear factor, x minus c, is a factor of f if and only if the remainder is 0 when you plug in that divisor, or when you do long division or synthetic division. So if f of c is 0, then x minus c is a factor of f, or x minus c is a factor of f if f of c is 0. So we can use remainder theorem to check again our process after we do synthetic or long division. And if both result in a 0, then that just verifies that our linear divisor is a factor of the actual polynomial. And if you get anything else other than 0, then it is considered not a factor. Okay. So 0, factor, not a 0, not a factor. Keep it simple, right? So let's go ahead and try factor theorem out below. So once again, we'll just set up for synthetic division. So here we have x minus 1. So we're going to start with 1, set up my synthetic division, and put in my dividend above. So I have 3, 2, 1, 0. All powers are accounted for. So 2, -1, 2, -3. 2 comes down, and then 2. Then you'll get 1, 1, 3, 3, and there we get 0. Perfect. We get a remainder of 0, which means that with the remainder of 0, this is telling us that x minus 1 is a factor of the original polynomial. But we can go ahead and use factor theorem to check that. So we can say f of 1, you'll get 2 times 1 cubed minus 1 squared plus 2 times 1 minus 3. And we'll just get 2 minus 1 plus 2 minus 3, which is going to give us 0. Checks out. And with that being said, since it checks out, we can say that x minus 1 is a factor of f of x. All right. Any questions on that process? Oh, and since it's a factor, we can rewrite it. If we were to rewrite it back into polynomial form, we would start off by writing the factor x minus 1, and then the broken down polynomial, the quotient of 2x squared plus x plus 3. So we broke it down by synthetic, but again, I'm just showing you things we're going to see later on today. All we have to know now is it a factor or not? Okay. Which means do it again for 3, x plus 3. So here, x plus 3, we have -3. And then 2, -1, 2, -3. Bring the 2 down. -6, add, -7, then 21, 23, and then what's that? -69. So -72. Okay, so here we don't get a remainder of 0. We get a remainder of -72, which is telling us that x plus 3 is not a factor of f of x. But of course, we can definitely double check it, because that's what factor theorem's about. We can check our work. All right, what's that? -27. So it's a -54 minus 9 minus 6 minus 3. That's -63, -69, -72. Checks out. But since it's not a remainder of 0, we say that x plus 3 is not a factor. Okay. Any questions on that?
If it is ruled not as a factor, there's no other further steps to go after this?
Good question. So coming up, I think on the next couple of pages is that, so we're
Okay.
going to be picking things called potential zeros, and we're going to be testing the zeros by synthetic division. If a zero doesn't work out, which means if we get a remainder, if we don't get a factor, this means we have to choose another zero to divide by. But for now, for these two examples, if it's not a factor, it's not a factor, we move on. All right. Okay. All right. So the next theorem concerns the number of real zeros that a polynomial function may have. In counting zeros of a polynomial, we count each zero as many times as its multiplicity. Okay. So the theorem, the number of real zeros. So a polynomial function cannot have more real zeros than its degree. So this means that if I said the polynomial function x squared, how many zeros could I possibly have? If I said x squared, how many zeros could I have?
1.
I could have one, but what's the max that I could have?
Oh, car giveaway 2.
Two, right? Could I have any more than 2?
No.
No, right? Because that's our theorem, right? A polynomial function cannot have more real zeros than its degree. So if it's x squared, I can't have more than 2 zeros. If it's x cubed, no more than 3. If it's x to the 10th, I can't have more than 10. So that's what our theorem is saying here. So remember that your degree tells you how many zeros you possibly could have, but you can't have more than what your exponent, your degree, your power states. Okay, which brings us into the next theorem. So full of theorems today. All right, we have rational zeros theorem. So let f be a polynomial function of degree 1 or higher of the standard form of a polynomial. So we go from, again, highest power to lowest power to constant. So we've seen this form before. Okay, where each coefficient is an integer, if P over Q in lowest terms is a rational zero of f, then P must be a factor of the constant, a sub 0, and Q must be a factor of the leading coefficient, a sub n. So this is just pulling the information from the polynomial above. So a sub 0, where's blue? There we go. This is our constant. And a sub n is our leading coefficient. And this all comes from the standard form of the polynomial above. A sub 0 is going to be related to P, and then a sub n is going to be related to Q. So what we're going to do with that is we're going to take all the factors of the constant, positive and negative, and put them over all the factors of the leading coefficient that are positive and negative. So we're going to take the constant, put over the coefficient, and find all the factors of every number. All right, it's a good time. So let's try it out. So list the potential rational zeros of the given function. F of x equals 2x cubed plus 11x squared minus 7x minus 6. Okay, so let's go ahead and start by labeling P. What is my constant in this given polynomial?
Six.
6. Good. 6 or negative 6, doesn't matter, right? I'll say, let's say negative 6. Now, give me all the factors of 6.
1, 2, 3, 6.
There you go. Positive and -1, positive -2, positive -3, and positive or -6. Okay. Q relates to my leading coefficient. What's my leading coefficient here?
2.
2. Give me all the factors of 2.
1 and 2.
1 and 2. Perfect. Now, all we're going to do is take all the factors of P and put them over all the factors of Q. So we're going to take 1, 2, 3, and 6 and put them all over 1, which means I'm just going to get 1, 2, 3, and 6. And then you're going to take 1, 2, 3, and 6 and put them over all the factors, or the last factor of 2, which is 2. So we're going to get 1 over 1, 1 over 2, which we don't have. You're going to get 2 over 2. Do we have that one?
Yes, 1.
Good. Then we're going to put 3 over 2. Do we have that?
No.
No. And then you're going to put 6 over 2. Do we have that one?
Yes.
Yes. Good. So what we have found are all the potential zeros that could possibly break the original polynomial down by synthetic division. So this means that if we were to try all these zeros in synthetic division, we would get 1, 2, 3, 4, 5, 6. We would have 12 tries to break it down. But when we get there, right now, we're just listing potential zeros. Any questions on that?
Just for like insanity purposes, because sometimes I have like a hard time keeping track of stuff. If we write a number twice, that wouldn't be like incorrect with the notation, right?
No, it
It'd
wouldn't
just
be.
be a little weird.
I wouldn't do it in my math lab, though. It might count you off.
Okay.
Yeah. No, good question, though. Okay. So those are the potential zeros, and those are the ones that we will throw into synthetic division to try and break down this polynomial, to try and factor it, which means I think we can get started with that already. So let's go ahead and try it out. Find the real zeros of the polynomial function 2x cubed plus 11x squared minus 7x minus 6, and then write it in factored form. Okay, so first off, what is the degree? What is the highest degree of this polynomial?
Cube 3.
Good. Now we know that we can only have 3 possible zeros that will work, right? But this time, well, for the next step, we want to list the potential zeros. And I believe this problem is the same one as above, but let's go ahead and just do it again for good practice. So P relates to the constant -6. We said all the factors of 6 are 1, 2, 3, and 6. And then Q relates to the leading coefficient, and all the factors of 2 are 1 and 2. Okay. Put P over Q, and we'll get, again, the same numbers as above. 1, 2, 3, 6, 1/2, and 3/2. There's our potential zeros. So like I said, we're going to get 6 tries to break down this polynomial function above. So here comes the fun part. Okay. So now in order to break this down, we are going to set up synthetic division.
12 tries.
Good. So what did I say?
You said 6. You're an
Oh,
accountant.
sorry. 12. Okay, so we're going to set up synthetic division and put in the polynomial. Make sure all powers are accounted for. We've got 3, 2, 1, and 0. So all that's accounted for. So I'm going to put those in. So we're going to have 2, 11, -7, -6. The 2 comes down. And, and now, out of these potential zeros, what number would you like to start with?
1 seems pretty straightforward.
Let's start with 1. Okay, that's always a good choice. Picking 1 is always a good start. So we're going to choose 1. 1 times 2, 2, we add, we get 13. 1 times 13, we get 13. -7 plus 13, we get 6. 1 times 6, we get 6 with a remainder of
0.
0. Hey, this means that 1 is a factor of the polynomial. Okay, so we did good. If we didn't get a 0 on the first try, then we would have to pick again from our list of potential zeros. Everybody good so far? All right. So now, since we got a remainder of 0, we're going to have to write this back into factored form. So the first factor we start with is, how do I put this 1, this divisor of 1, back into linear form of x minus c? What would I write?
X plus
Minus
1.
X minus 1,
Minus plus 1.
right? And then what goes next to it is our quotient. So remember, when we do synthetic division, we reduce the powers by 1. So when I rewrite the quotient, what am I going to start with?
2x squared plus 13x plus 6.
Very good. 2x squared plus 13x plus 6. Okay. And now we have to see if we can break this polynomial down more. So what we have just put this broken down polynomial, so the term for this broken down polynomial, it's actually pretty funny. After you break it down once, it's called the depressed polynomial.
I feel you, buddy.
Which means we're only going to make it more depressed by trying to break it down more. Sounds funny, right? Okay, so here we have an actual option. We're going to take this polynomial. Oop, come on. We're going to take this polynomial, and we can either try and factor it now, or we can throw it back into synthetic division. What do you guys want to do?
If we throw it back into synthetic division, will we have to look up potential zeros again, or would we simply just use the ones that we've already identified?
Very good question. So we don't have to look for more potential zeros. We get to use the same ones from before. So if we throw this back into synthetic division, we get 12 tries all over again. So up to you guys. You want to see if it's factorable, or do you want to throw it into synthetic?
Synthetic.
Go synthetic? Okay. I like it. So let's throw it back into synthetic then.
Okay. Couldn't we use the AC method on this pretty easily?
We don't use AC in this class.
Okay.
What is AC?
Don't worry about it.
Okay.
It's for business majors only.
Oh, yeah. Okay.
That thing that I got A's with all the way through calculus 1 that apparently is too dumb to use.
I know,
I'll
right?
show you guys. I'll show you guys in a second, but yes, well, here we're just doing our options right now. Okay, so we have decided to throw this back into synthetic division. 2, 13, and 6, where the 2 comes down. Don't worry, I'll answer everything today. And now you get 12 choices all over again. So what potential zero would you want to try this time?
2.
Try 2. Let's try it. Let's try a 2. Positive 2. If we do that, I get 4. I get 17. Oh no. I get 34 and I get 40 as the
40
remainder.
is
So
not as
if 2 didn't work out, then go ahead and try
6.
6. Ah, I like that.
Negative 6.
Go negative 6. Let's try
Positive 6. I don't
that. Pick one.
negative 6.
Let's go negative 6. All right, let's try that out. Negative 6. This will give me negative 12. We're adding. Here we'll get 1 and then negative 6. Hey, look at that. You get a remainder of
0.
0. All right. Okay, which means let's go ahead and rewrite the next depressed equation. And you can't forget about the first factor. We can't forget about the x minus 1 that we started with. And now you have to rewrite the negative 6 as a linear form. So what would you write there?
X plus 6.
X plus 6. And then how would you write the quotient?
2x plus 1.
2x plus 1. There you go, guys. Can we break these down anymore?
No.
No. This is it. We have taken a polynomial that looked unfactorable from the beginning, and by using potential zeros and synthetic division, we have been able to factor it. Crazy, right? Okay. And a fun part about this is if you set your final answer equal to 0, it's going to tell you what zeros would have worked from your potential zeros. So let's see what that looks like.
That's
So if I were to set
1,
the-
negative 6, and negative 1/2.
There you go. And what was the degree of our polynomial?
3.
3. Do you see 3 zeros there?
Yep.
So from our 12 choices, these are the only 3 that would have worked. So we honestly, we could have thrown the 2 and the 1 back into synthetic division and used negative 1/2, and it still would have worked. Crazy, right? So if I put that 2 and the 1 there and did negative 1/2, negative 1/2 times 2 is negative 1 with the remainder of 0. So there's another possible answer for this. It would be x minus 1, x plus 6, x plus 1/2, and that 2 just has to wait on the outside. These are both equivalent answers. Crazy, right? Okay. But let's go ahead and look at some factoring strategies, right? Because this part, 2x squared plus 13x plus 6. We could have factored this 30 minutes ago and been done. So here you have plus plus. So this means you'd have 2x plus a number and x plus a number. And what are the factors of 6 that could get me close to 13?
1 and 6.
1 and 6. So I'd put a 1 here and a 6 there, and it'd be factored and we'd be done already. Fun, right? But then let's go ahead and show this AC method. Ooh. Okay. If you guys really want to know it. So AC method, remember that these are in the form of ax squared plus bx plus c. It's killing me with the feedback. So this means you take a, which is 2, and multiply it by c, which is 6, and gives me 12. Well, now you're going to list all the factors of 12. 1 and 12, 2 and 6, 3 and 4, and I think that's it without repeating. And you're going to look at this list of factors and tell me which ones can add to give you 13. And that's just going to be 1 and 12. So that means that you take 1 and 12 and you rewrite this as 2x squared plus 12x plus 1x plus 6. And then you factor by grouping, which means I'd take a 2x out, and that would leave me with x plus 6. I'd take a 1 out, which would leave me with x plus 6. And then this would factor to x plus 6 times 2x plus 1. Same thing. If you factor that way, cool, but not cool. But that's just a foolproof way of factoring. Any questions on that?
I do have a question on the potential zero stuff.
What's up?
So let's say, you know, our like kind of potential like maximum is 3, but what if like our maximum is like 2, for example, and we get like 3 of you know, these factors? Do we have to go back and test like, hey, this maybe doesn't work, or is it kind of like a foolproof since, you know, this is 0 and must be in there, like the remainder is 0, so it must be
So
in there.
remember, by the theorem, you can't have more zeros than what your degree states. So if your degree was 2 and you're ending up with 3 zeros, that's not good.
Okay,
So this means you would definitely want to go back and check your work.
got it.
Okay. All right. Fun times. All right. Next one. Find the real zeros of this polynomial function. X to the 5th minus 5x to the 4th plus 12x cubed minus 24x squared plus 32x minus 16. Blah. Wow. Does that even look factorable? Not at all, but we're going to do it, right? So what is the highest degree here?
The 5th.
5, which means our final answer should have about, hopefully, 5 zeros. No more than that, right? Okay. And then we're going to list our potential zeros. So P belongs to the constant, which is negative 16 or 16, doesn't matter. And you list all the factors of 16. 1, 2, 4, 5, no, 6, no, 7, no, 8, and then 16, right? I didn't miss any. And then Q belongs to the leading coefficient, which is just 1. Hey, lucky day. Plus or minus 1. Then you put P over Q and put all of P over 1, and lucky us, we just get 1, 2, 4, 8, 16. Okay. Now let's set up for synthetic division. All powers accounted for. 5, 4, 3, 2, 1, 0. Yes. So 1, -5, 12, -24, 32, -16. Right? 5, 4, 3, 2, 1, 0. And the 1 comes down. All right. Well, we got 1, 2, 3, 4, 5. We get 10 tries. What number would you like to start with?
One.
1? Let's start with 1. 1 times 1 gives me 1. -5 plus 1, that's -4. 1 times -4 is -4. 12 plus -4 gives me 8. 1 times 8 is 8. And I get -24 plus 8, which gives me -16. And then -16 times 1, you get 16. And then 16, you get 0. Wow. Did that work out nicely?
Yes.
For sure. Okay, so let's go ahead and write the first depressed form. So with that divisor of 1, what do I write?
X minus 1.
X minus 1, and then the quotient.
X to the 4th minus 4x cubed plus 8x squared minus 16x plus 16.
Woo. All right. So we have to keep going, which means we're going to have to break down this polynomial, this new depressed polynomial again. And unlucky for us, it's not 4 terms. If it was 4, we could factor by grouping, but since it's 5, we have to throw it back into synthetic division. And we get 10 tries all over again. One, -4, 8, -16, 16. So 1 comes down. And out of our factors, what number would you like to choose this time? Stop it. Why are you doing that?
-4.
-4. Let's do it. -4. Let's see. -4 times 1 is -4. This will give me -8. This will give me 32. Oh boy. That'll give me 40. That'll give me -160. Should I stop?
It might work out in the end. It might work out.
-176. Oh my goodness.
How about we take that -4 and just turn it to a 4? Call it a day.
All right. So -4 didn't work out. But you see, that's the fun part. You choose and you get practice. Did you get it right or not, right? So, all right. So we're going to go with +4 this time. So 4 times 1, you get 4. You'll get 0. You'll get 0. You'll get 8. You'll get 32. And you'll get 16, but then you'll get 64. Ooh. Did that one work out for us?
No.
No. So this means, hey, but this is good news because this means that 4 and -4 are out. So what other number could we go with?
-1.
-1. Let's do it. -1 times 1, -1, -5, 5. You get 13. -13. You get -29. Should I stop?
Did we do 2 already?
We have not done 2.
No.
Don't want to try 1?
Well, we already did 1, right? The last one?
No,
Would
you
could it be in
choo-
there twice?
Yeah, you could choose it again.
Oh.
That's why I said you get 10 picks all over again. So if you choose 1, I mean, we'll go with 1. That means you'll get -3. -3, you'll get 5, you'll get 5, you'll get -11, and we can stop there, right? So this means 1 and 4, those are out, which means I heard it already. Let's move on to 2, right? Let's see if that's any better.
Didn't we already try to?
No, we have not tried
No?
2
Oh,
yet.
sorry.
We only did 4s and 1s. So we'll try +2. And that'll give you -2. That'll give you -4. That'll give you 4. This will give you 8. That'll give you -8. That'll give you -16. Woo!
We have achieved 0.
We have achieved 0. All right. And now, time for more depressed equations. So start off with the first divisor that we used, x minus 1. And now how do I write that 2?
X minus 2.
X minus 2. And how do I write the quotient?
X cubed minus 2x squared plus 4x minus 8.
There we go. Okay. Here we are. We're at the crossroads again. Do we try and factor it, or do we throw it back into synthetic with 10 more tries?
Factor. Factor, for the love of God, factor.
All right, let's see if it works out for us. It's a bold move, Cotton. All right. So this is 4 terms. So what is the only way to factor a 4-term polynomial?
You got to separate them.
Good. So we'll separate these 2, separate those 2, and then from x cubed minus 2x squared, what could I factor out?
X squared.
X squared. That'll leave me with x minus 2. And from 4x minus 8, what could I factor out?
4.
A 4. That leaves you with x minus 2. Hey, look at that. Which means, since these look the same, I can do what with those?
Factor them
Combined,
out.
so you got, yeah,
Factor them out. So I get
another x minus 2.
another x minus 2. And what's left over?
X squared plus 4.
X squared plus 4. All right. Look at that. Which means let's go ahead and clean this up. I have 2x minus 2's. So I can rewrite this as x minus 1 times x minus 2 squared times x squared plus 4. Can you factor x squared plus 4?
Yes.
How so?
Would it be just x plus 2, x plus 2? Or actually, I'm
'cause
wrong. No,
that would be
would
x
something
squared
else.
plus 4x plus 4. So no, you can't.
No.
No, because it is a sum of squares, right?
Yep.
If it was x squared minus 4, could you factor that?
Yes, because it's a
Yes.
difference of squares.
It's a difference of squares. Good.
That's what I got confused with.
No, it's all right. It's that sign, man. Okay. So this means that we have completely factored the polynomial above. And what zeros would work that we found if we set this equal to 0? X equals 1 and X equals 2. Guess what though?
The last
If
one.
we
No, you're right.
go ahead. What?
I was confused.
So if we threw it back into synthetic division instead of factoring, this means 2 would have worked again, because how many times does 2 show up? What is the multiplicity on 2?
It's 2. It's
2.
squared.
Good. So if we use 2 once, that means we could use 2 again, and when it would have worked. All right. But now for some crazy stuff. What if you set x squared plus 4 equal to 0 and solve for x?
You would get a positive and a negative 2.
Careful. What happens when you square root a negative?
Imaginary numbers.
You get imaginary numbers. So I would get x equals plus or minus what?
2i.
2i. And believe it or not, these would work in synthetic division as well. But do you see them anywhere in your potential zeros?
No.
No. But what was our degree?
5.
5. Do you see 5 zeros? Remember to count
No.
multiplicities.
Oh yeah.
Oh,
2,
yes.
4, 5.
There's 1 0 here,
2, 3.
2 zeros here, 2 zeros there. Total of 5. But 2 of them are imaginary. Now, for this section, you're not asked to find imaginary numbers. I'm just showing you because in the next section, we will be using imaginary zeros and finding imaginary zeros. Just to get your brain working on a Monday. By all means, though, try to plug 2i in synthetic division and try it out on your own. It's a fun time. All right. Any questions on this problem?
Not a question on really this problem, but like the overall steps and everything. Is it just simply that you just have to plug in, see if it works, plug in, see if it works, or is there like straightforward method to basically discount the ones that are not supposed to work? Or is there steps to do
Ooh,
that?
Very good question. So to help you guys out, so you're not just like guessing numbers, right? I mean, it's great practice. It gets you better at multiplication and whatnot, but we did learn factor and remainder theorem for a reason, right? So let's go to Desmos to have some fun. I don't even have it open. Whoa. Is it that Firefox? I don't even know. All right, one moment. Not now. Desmos, not the right browser. There we go. Graphing calculator. And let me bring that to the side. Keep you there. And didn't want to do that. Okay. So this could save you time. But remember, you still have to show your work. You still have to use synthetic division and all that. But I'm going to type this function in. X to the 5th minus 5x to the 4th plus 12x cubed minus 24x squared plus 32x minus 16. Okay, now I'm going to pull up the table that's on Desmos. So if you hit this little gear icon above what I wrote, you'll see it gives you a table option. Click on that. And now, looking at our potential zeros over here, I'm going to type them in. And if I get 0 as an answer, that means that's the one I'm going to use in synthetic division. So let's do 1. Oh, messed it up. That's an X. I'll do 1, -1. I'll do 2, -2, 4, -4, 8, -8, 16, -16. And now look at your Y values. And you see the Y values that are 0. That means that I can use 1 in synthetic division, and that means I can use 2 in synthetic division. Instead of just, hey, let me keep guessing numbers, you can try that out. So hopefully that helps you out. If not, just keep picking and choosing. Any questions on that?
So understanding that we have to show our work, we are
Yeah.
allowed to utilize
So-
this tool.
Exactly.
Okay.
So let's say you're using this tool, right? So you found out that 1 would work because you get a remainder of 0. That means you would then apply synthetic division and use 1 in synthetic division and do the breakdown. Basically, everything that I'm showing on this paper is how your work should look.
Okay, sounds good.
Sound good? So that little
Sorry.
calculator trick just helps you find the 0 to use in synthetic division.
My bad. I keep forgetting my mic on off mute.
You're good. All right. All right. Everybody good with that? Okay then. All right, last one. Graph the following polynomial function. So this problem includes everything we've learned in this chapter so far. So it wants the end behavior, x-intercepts, y-intercepts, multiplicities, turning points. Does it touch? Does it bound? Does it touch? Does it cross? Everything. So in order to find your intercepts, your x-intercepts, and your multiplicities, you're going to have to break this down by learning what you've seen today by potential zeros. So let's see. So the function is 4x to the 5th minus 20x to the 4th minus x plus 5. So first thing we want to do is determine the end behavior. So remember, end behavior is all about the exponent, the leading exponent, and the sign of the leading coefficient. So for A, what is the largest exponent we have for this problem?
5.
5. Good. So degree or exponent is 5, which is odd. And then what is my leading coefficient?
4.
4, which is positive. Okay. Now, if I have an odd degree, but a positive leading coefficient, what does my end behavior look like?
Yeah, going left to right, you look like you're making an angle down.
So it would go down this way.
Opposite way.
You sure? Odd positive.
Yes, that's right. Yes, down that way. Boom, boom.
So that would be your end behavior. Okay. So now we know how our end behavior looks. So now the next thing we have to do is find the x-intercepts. But in order to do that, we're going to have to break this polynomial down by what we learned today. right, so B. Okay. Well, we're going to find the x-intercepts, but in a moment, let's see. Let's go ahead and list off potential zeros. So P belongs to the constant, which is 5. And the only factors of 5 are 1 and 5. And then Q is the leading coefficient. So we get plus or minus 1, 2, and 4. And then P over Q, we get plus or minus 1 over 1. So 1, and then 5 over 1. So 1 and 5, and then you get 1/2, 1/4, and then 5 over 1, 5 over 2, and 5 over 4. Gross. Okay, so those are our potential zeros, which means now let's go ahead and set this up for synthetic division. Make sure you have all powers accounted for. So 4, so and then 5, 4, we're missing x cubed and x squared. So this would be x cubed, x squared. Here's x, and there's 5. Okay, and out of these potential zeros, what number do you want to go with?
Uno.
Uno. Let's try it. Let's try it. So 4. So yeah, you get 16, negative 16. And then you'd get negative 16, negative 16, negative 16, negative 16, negative 16, negative 17. Is this going to work out?
No.
No. All right. If not 1, then maybe try
-1.
Yeah. So -4, negative 24, and then 24, and then negative 24, negative 24, and then 24. You get 23. That's not going to work out. So that means 1s are out.
And now we use Desmos, right?
And now we use Desmos. You guys can use Desmos. I showed you the trick. But what else? What's
5.
another good number?
5 over 4.
5 over 4? Ooh, risky fraction, man. 5 over 4 times 4 is 5. You get negative 15. 5 over 4 times negative 15. That's what? Negative 75 over 4? Should we just stop?
Oh, this could work out.
Yeah. I'm going to stop there. I mean, we could try negative 5 over 4. If you did that, then you'd have negative, what's that? Negative 5, so that'd be negative 25, and then that'd be positive 125 over 4. Yeah, that's not going to work. Hey, so 5/4 is out. What else you got?
Cassie just said to try 5.
Try 5. Okay. 5 times 4, you get 20. And look at this. 0, 0, 0, 0, 0, 0. -1, -5. Oh my goodness. She did it. Which means we'll get our depressed form of x minus 5. And how would I write the quotient?
4x to the fourth minus 1.
Good. 4x to the fourth minus 1. Can you factor 4x to the fourth minus 1?
Not really.
Saying not really means we throw it back into synthetic. Is this a difference of squares?
No.
Yes.
Is
Yeah.
4 a perfect square?
Yes.
Is 1 a perfect square?
Yes.
And x to the fourth is definitely a perfect square.
Yes. X squared squared. So 2x squared squared.
What?
2x squared squared.
2x squared minus 1 and 2x squared
+1.
plus 1. Wow.
It's only the difference of squares as long as it's a so-and-so -1, not a +1.
Exactly.
plus
If that was 4x to the fourth plus 1, we would have been done.
Okay.
You can
Okay.
still get 2 more zeros out of this. They're just not rational.
Yeah. Oh, God. Okay. Well, we can't factor anymore. So this is the factored form. But remember, we're still solving for x-intercepts. So now we have to set all 3 of these equal to 0 and solve for x. Ooh, this is ugly. All right. So this means first one's given. You get x equals 5. Yeehaw. Next ones are going to be a little bit tougher. 2x squared minus 1 equal to 0. And 2x squared plus 1 equal to 0. All right. Solve for x on these. 2x squared equal to 1. Divide by 2. X squared equals 1/2. But then you have to square root both sides. And we're going to get x equals plus or minus, and this will become square root 1 over square root 2, which becomes 1 over the square root of 2, which becomes square root of 2 over 2. Oh boy. Okay. And there's those x-intercepts. Are we going to get x-intercepts from the last ones?
They'll be imaginary, right?
Good. You'll get imaginary numbers, which means we don't have to worry about them. So that'll be all imaginary. Oof. Okay. And I can make this smaller. There we go. Okay. So we have our x-intercepts, which means all we need is our y-intercepts. And the y-intercept is always the easiest because when you find a y-intercept, you let x equal 0. So if you let x equal 0, that's 0, that's 0, that's 0. And what's our y-intercept?
5.
5. Oh, so easy. Too easy. All right. So I'll just put that down here. Okay. Hard part's done. Now all we have to do is determine multiplicities, turning points, and graph it. All right. So for my zeros, I'll zoom in. Let's see, right there's perfect. Or no, right there. Stop it. I'll put them on. I'll write it out here. So for my multiplicities, you have x equals 5. How many times does that show up?
Once.
Once. So this has a multiplicity of 1, which means it will cross or touch.
Cross.
Cross.
And then you have x equals plus or minus. So this means you have x equals square root of 2 over 2 and x equals negative square root of 2 over 2. What are the multiplicities on these zeros?
They'll cross.
They're cross. So that means they both have a multiplicity of
1.
1. Good. Cross. Okay. There's multiplicities. And then the other part is turning points. What was the highest degree?
5.
5, which means how many turning points do I have?
4.
4. 4 possible turning points. Okay. So we have everything out of the way, which means we can now graph. What is the decimal number for square root 2 over 2?
Oh, it's like 0.7 something.
Yeah, 0.71. All right. So let's go ahead and graph these. All right. 0.71, positive 0.71, which I'll put around here. Oh, come on. You don't want to plot stuff? Oh, it's not even big enough. There we go. Stop it. It's broken. Draw. Oh, there we go. Bigger. Too big. There we go. 0.71, negative 0.71. Let me erase that. That one's bad. And then what was it? 5? 5 was the other one. And then the y-intercept at 5. 1, 2, 3, 4, 5. There we go. Okay. And now from our end behavior, we open bottom left. Ooh, look at that pink. We open bottom left, come up, go cross, come down, cross, bounce around, and there we go. Bingo. And that was like 5-1 and 5-2 and 5-6 all in one lesson, on one problem. Crazy. All right. I think that was the last one. So any questions on this last problem? That was a lot of information. But now you guys know how to factor the unfactorable, or what looks like it's unfactorable. All right. Other than that, we are done. If we got questions, stick around.